So it's our pleasure to listen to Barbara Opozda about curvature inequalities and Simon's type formulas in statistical geometry.
Thank you. Simons proved his first famous formula for hypersurfaces in the Euclidean space Rn. Then the formula was improved, generalized, new formulas appeared, and that first formula said, roughly speaking, about a relationship between the Laplacian of the second fundamental form and the mean curvature. Now, the formulas of Simon's type are important tools in Riemannian geometry. I like to present some applications of such formulas, one formula, to statistical structures. Independently, I like to say something about inequalities for curvatures in statistical geometry. So this one doesn't work. Yeah. Oh, okay. Let me first introduce notations I will use in my talk. M will stand for an n-dimensional manifold. G will be a metric tensor field on M, and we'll have a torsion-free connection nabla on M, and a pair G nabla is called a statistical structure if the cubic form nabla G is symmetric. Nabla is the statistical connection of the structure. We have the dual connection, which will be denoted by nabla bar. The Levi-Civita connection for G will be denoted by nabla hat. We have the difference tensor K, and K is the difference between nabla and nabla hat. It's written in one or the other way, but anyway, it's symmetric for X and Y. And we have the cubic form A. A is defined on the third line from the bottom. A of XYZ is G of KXYZ. It's symmetric for all XYZ. And we have two cubic forms, but they are the same, almost the same. They give the same information. Nabla G is equal to -2A. And a statistical structure is called trivial if and only if nabla is equal to nabla bar. So this is the definition, and it's equivalent to the fact that the difference tensor is 0, or C vanishes, or A vanishes. And now, okay, so we have the one form tau defined as tau of X is the trace of Kx. It's called the Chebyshev form. The name is from affine differential geometry, which is older than the theory of statistical structures. But in the book of Shima, it's called the first Koszul form. We have the corresponding vector field E, which is just the trace of K relative to G. We have trace-free statistical structures, and a statistical structure is called trace-free if now a tau is 0. R, bar, R hat will stand for curvature tensor, for nabla, nabla bar, nabla hat, respectively. A statistical structure is Hessian if and only if R is 0. We have the corresponding Ricci tensor, Ricci bar, Ricci hat, and we can produce scalar curvatures. Of course, we have the standard scalar curvature for G, and it will be denoted here by rho hat, but we can also define rho as the trace of Ricci relative to G, and this is the scalar curvature of nabla. The same we can do for nabla bar, but we get the same. So we have two scalar curvatures, rho hat and rho. We also have the following curvature tensor, which I denote by the bracket KK, and this curvature tensor as a tensor of type 1,3 is defined as by using the commutator of Kx and Ky, as you see in the third line from the bottom. Okay. It's a good curvature tensor. It has the same algebraic symmetries as the Riemannian curvature tensor. The following formula holds in affine differential geometry is called the theorema egregium. So it's a relation between rho hat and rho. We have two other components, the square norm of A and the square norm of tau. We also have some relations between the Ricci tensors. You see the formula number 3, and we have this important trace-free case, and then we have the inequality okay, so the Ricci tensor of G is greater than or equal to the arithmetic average of Ricci and Ricci bar. So this is a model inequality for curvature tensors, okay? But it's only in the trace-free case. It looks so nice. But we'll go back to this. Now let's go on. As in Riemannian geometry, we define a 0,4 tensor field now for the connection nabla, so for R. But this tensor field is not skew symmetric for Z and W in general. We have some relation. When we interchange Z and W, then we get, we should take R bar, okay? The following conditions are equivalent. This 0,4 tensor is skew symmetric for Z and W, even only if R is equal to R bar, or if nabla hat K is symmetric as 1,3 tensor field. Equivalently, nabla hat A is symmetric as a 0,4 tensor field. If a statistical structure satisfies one of the above conditions, it's called conjugate symmetric. The class of conjugate symmetric statistical structure is very big. Even in a fine differential geometry, which is really very particular, but we should always remember about this geometry because we have a lot of examples there, a lot of theorems, so we should always resort to a fine differential geometry. But even in that case, this class is very, very big. Oh. Okay, now we can define a new curvature tensor. I denote it by R calligraphic, and it's just the average of R and R bar. And it's a good curvature tensor, namely, if we define this 0,4 curvature tensor, that it is skew symmetric for Z and W. And because of that, we can produce a sectional curvature, which we do, and I'll call it the sectional nabla curvature. For a conjugate symmetric statistical structures, we have the equality that R is equal to R. R calligraphic is equal to R, okay? If a conjugate symmetric statistical structure has constant sectional nabla curvature K, then R is equal to KR0, where R0 is that easiest curvature tensor. And if the dimension of M is 2 and a statistical structure is conjugate symmetric, then R is equal to KR0 with K being a function. Of course, if R is equal to KR0, then the statistical structure is conjugate symmetric. If N is, if N is greater than 2, then K is automatically constant for conjugate symmetric statistical structures. Okay, so I will also use the expression that a statistical structure has constant curvature K, which means exactly that R is equal to KR0. A Hessian structure, of course, has a vanishing constant curvature. Okay, did I go too far? Yeah, okay. Now, oh, it goes without me. Mm-hmm. Okay. It's sufficient that I look at it. It's kind of okay. Sorry, it's very sensitive. Okay, now I'm going back to the first inequality for Ricci tensors. Maybe you remember. And if if a structure is not trace-free, then we have an additional term, which vanishes if a structure is trace-free. But if it's not trace-free, then, well, we don't have anything by now, but we can prove such an algebraic inequality, which is about this term. This term on the this term on the left-hand side is exactly the term which we had for the Ricci tensors, and we can prove this inequality. On the right-hand side, we have the squared norm of tau, of the one form tau. And from this, we can get new inequalities for the Ricci tensors. The first inequality is for any statistical structure. The second one is for statistical structures with constant curvature K. And the last one is for Hessian structures. Now, we have two important objects, the cubic form and its trace, more or less the trace. So the one form tau. And we have this algebraic inequality, and using this, we can go, and using the theorema egregium, we can prove inequality for the difference between rho hat and rho, between the scalar curvatures. And the first inequality here says on the right, in the first inequality on the right-hand side, we have the squared norm of A, and in the second one, the squared norm of tau. And using this, we can formulate some inequalities for statistical structure with constant nabla sectional curvature K, and also for Hessian structures. The last two inequalities are for the Hessian structures. Okay, so the first one in terms of tau, and the second one in terms of A. Now let's go to Simon's formula. Here I formulated this formula, I wrote this formula for tensor fields of type 0R. So we have a Riemannian manifold, and we have a tensor field S of type 0R, and the following Simon's formula holds. On the left-hand side, we have the squared norm of our tensor field, and it's Laplacian. It's the usual Laplacian. And on the right-hand side, we have the last term, which is the squared norm of nabla S, the covariant derivative of the tensor field. And we have this first term in which we have, again, some delta. And this delta is another Laplacian. Even for one forms, it's not the Hodge Laplacian. And the definition of this Laplacian is given in the formula 21 years. We take the second derivative of the second covariant derivative of S, and we take the trace on the first two places relative to G. We can start with one forms, and for any one form tau, we compute this second covariant derivative and take the trace, and we get such a formula. And then where delta here is the codifferential, and then using Simon's formula, we get such a Simon's type formula from which we can derive, for instance, the classical Bochner theorems. Now we can apply it to our one form, let's say the Chebyshev form, and we get such a theorem. Let the G nabla be a statistical structure on a manifold M, and tau be its Chebyshev form. Assume that nabla square tau, nabla hat square tau is 0, and tau is constant, or M is compact. And moreover, the Ricci tensor of the metric G is non-degenerate at a point of M, then the structure must be trace-free. No, five.
Okay.
Now, let's apply our Simon's type formula to the statistical cubic form A, and we can compute the right-hand side, that Laplacian of a tensor field in various ways. And here I gave 3 formulas. So on the left-hand side, we always have the Laplacian of the squared norm of A. On the right-hand side, we have the first term and the second. They are everywhere the same. And then we have various expressions, but we always have a curvature tensor, Ricci tensor, and so on, okay? So, and now we can use such formulas and prove, for instance, such theorems. Let G nabla be a statistical structure of a non-positive constant curvature on a compact manifold M if Ricci is non-negative and nabla hat square tau is 0, then the metric must be flat and nabla hat A is 0. So the easiest case, but trivial, is when A is 0. And the second step is the case where nabla hat A is 0. And even in the theory of affine hypersurfaces, this condition was studied for many years before getting the full classification of such a hypersurface in very special cases. And we can receive other theorems. So I go on. And now let's look at this function, the squared norm of A. Here I put some two inequalities proved by Blaschke, Calabi, and Armin Lee. So in the middle, we have the Laplacian of U. On the right-hand side, we have some expression with, depending on U, the dimension, f this portion nabla hat A norm squared. On the left-hand side, we have the same things, but of course different in general. And now for studying complete metrics, one can use the following Gauss maxim principle. So here is the principle, probably you know it. And here is a theorem due to Calabi, in fact. So if G nabla is a trace-free statistical structure with R equal to K R0 and complete G on a manifold M, then if K is greater than or equal to 0, then the structure must be trivial. If K is constant and negative, then the Ricci tensor of G is negative, semi-definite, and we have such an inequality. And usually this portion, this term, the squared norm of nabla hat A is regarded as just non-negative. But we can also take into considerations the infimum of this function and the supremum, and we can get some more delicate estimations. So here is an example of such a theorem. We have a trace-free statistical structure, and R is equal to K R0. I repeat that we have a lot of examples, and we know that the class is huge of such manifolds. And if G is complete, then and the supremum of this function is bounded from above by this number, which depends on K and N, then we can say something about the infimum of U and the infimum. The same we can do for the infimum of this theorem is even better. For the infimum of nabla hat A norm squared, and the supremum of U. So these are examples of applications of Simon's type formula to statistical structures. Thank you very much.